Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on December 10th, 2025, about 3 days ago. It shows that with better training, gradient-based planning can match or beat the classic cross-entropy method, while using only about 10% of the planning time, giving roughly a 10-time speedup. The paper is titled, Closing the Train Test Gap in World Models for Gradient-Based Planning. And as we will see later, the implications for how we train and deploy world models are quite significant. The introduction just framed the overall train test gap. Figure 1 now illustrates how the two fine-tuning strategies address it inside the world model's latent space. The left panel shows online world modeling, where orange predicted trajectories wander outside the blue expert distribution, and green corrected trajectories pull them back using the real simulator. The right panel shows adversarial world modeling, where red adversarial trajectories deliberately push against the blue expert path to expose weak spots. The legend clarifies that both methods expand reliable coverage in latent space, so gradient-based planning becomes more accurate and robust. Alright, Figure 2 compares how the planning loss landscape looks before and after adversarial fine-tuning on the push-T task. The left panels for the original DINO world model show jagged contour lines and a bumpy three-dimensional surface, which signal many narrow valleys and poor local minima for gradient-based planning. The right panels for the adversarially trained model look much smoother, with wide contours and a broad basin around the optimum. That broader, gentler valley means gradients point more reliably toward good action sequences, so optimization becomes easier and more stable. Figure 2 highlighted how adversarial fine-tuning smoothed the loss landscape, and Table 1 now shows the payoff in actual task success. The table reports success rates for 3 domains, push-T, point maze, and wall, under open loop and model predictive control settings. Adversarial world modeling with gradient-based planning almost always beats the original DINO world model, and in many cases even matches the cross-entropy method while being far faster. Online world modeling also helps, but adversarial training delivers the highest gains, especially for the harder wall task, where success under model predictive control jumps to roughly 94%. Well, Table 1 quantified success rates, and Figure 4 now measures how prediction error shifts between expert and planning trajectories on push-T. The horizontal axis reports training minus planning error, so negative values mean the model behaves worse during planning. The gray bar for the original DINO world model sits slightly negative, showing a harmful train test gap. The light green online world modeling bar turns slightly positive, and the dark green adversarial world modeling bar jumps strongly positive, indicating much more reliable predictions for planned action sequences. So, Figure 3 turns from error gaps to raw planning speed on the push-T task. The curves show success rate versus wall clock time, and the overview makes clear that gradient-based planning reaches high success within just a few minutes. The legend box separates DINO world model, online world modeling, adversarial world modeling, and the 3 optimizers. The right side of the plot highlights that the cross-entropy method only catches up after hundreds of minutes, so it is dramatically slower for similar success. Alright, the previous figure focused on speed, and Figure 9 now probes how sensitive performance is to the adversarial training hyperparameters. The 2 heat maps show success rates on the wall task as the scaling factors for actions and visual latents vary under fixed and adaptive perturbation radii. Most squares stay deep green for lambda values up to about 0.2, which means planning remains highly reliable across a broad range. Only when the visual scaling factor lambda z approaches 0.5 or 1.0 do success rates collapse, especially in the fixed setting, indicating overly strong visual noise breaks the world model. So, the big message is that better training, not a new planner, makes gradient-based planning actually work. Online rollouts and adversarial perturbations close the train test gap and let fast gradients rival slow sampling. That shift could make world model planners practical for richer, real robots. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.